Okay, you guys ready? Did we have 17 people at one point?
What was that?
17
17
people.
on our
No,
participation list.
Oh, I'm not sure.
Okay, so let's see. It's Alan, Brian, Jetsy, and Kirsten, sorry.
Kristen.
Kristen. Okay, I'll get it right. I'll get it right. And it's not
Just-
that hard, right?
No, just call me Chris. Honestly, everyone calls me Chris, so yeah.
Okay, so let's have you guys do PC5. Let's see. And we'll have Alexandria, Cheyenne, and Kevin. You guys do CL6. And we'll have Hector, Norma, and Steve do PC3. You guys are going to write on my board and explain it?
Yeah. We don't have to go like one. Oh, okay. So someone else is drawing. That makes me feel better. Oopsies. Okay, I don't know if that's right, but
That is correct.
awesome.
That is correct, Hector. Lovely. Good job. So, piece of cake?
Yeah.
Yep.
Yeah.
Yeah.
Okay, good. Okay, so we've talked about formal charges.
I think we barely started talking about it when we were ending class last time.
Okay, so if you guys remember the definition, formal charges are equal to valence electrons minus lone pair electrons I'll put this AKA, also known as non-bonding electrons, minus bonds. And your goal is, when you're doing your Lewis dot structure, to find out whether or not that structure is going to be more likely or not, is to try to minimize it so that all your values are 0 or really, really close to 0. Okay, so you do this for each of the atoms. So for instance, start off with this first C. So if we do the formal charge on this first C, what is the value? What is the number of valence electrons?
8.
For valence electrons, not electrons surrounding the atom. Valence
Oh,
electrons, carbon.
4.
4. Minus number of lone pair,
0.
number of bonds,
4.
and that equals,
0.
okay. What about this carbon here?
4. 0.
Number of lone pair electrons,
0.
number of bonds,
4.
this oxygen,
6.
number of lone pair electrons,
4.
number of bonds,
2.
and hydrogen. Number of lone pair, valence electrons, valence electrons,
So,
lone pair, and bonds.
1.
Okay, so this is an example, 0, 0, 0. So that's a good structure. What about PCl5? Let's do the center atom, because all the other ones we just have to do one time. So for the phosphorus, Kevin, what is the number of lone valence electrons for phosphorus?
5.
Number of lone pair?
2.
This one right here.
Oh, 0.
Number of bonds?
5.
Okay, and our Cl, Norma.
Wait for CL.
Yep, number of valence electrons?
I just drew a blank. Valence electrons are the I can't count today. Give me a second.
It's okay, it's
I
a
have to look
Monday.
on- yeah, I have to look on, like for me, I have to look on the periodic table.
Okay,
For CL. Is it 7?
okay. Number of lone pair electrons?
Isn't that just, ugh, I'm counting too much. 1, 2, 3? Or do I have to count both of them?
You have to count both of them, so,
Ah, okay, there's my answer. 6.
okay. And number of bonds?
It'd just be 1, right?
Yep,
Yeah.
we have that together, 0. So all of these are exactly the same, so it'd be exactly the same there. So then that shows us that that would be the optimal structure for it, okay? Because we have a very low formal charge. Okay, so your homework assignment actually asked you quite a bit about formal charges. So, okay, questions, concerns, Cash?
No, no. Wait, yeah, now.
Okay, sorry about that.
It's fine.
Okay, so who's gonna be senior Adam?
Carbon?
Okay, so got carbon in the center. How many valence electrons does carbon have?
4.
What about each of those oxygens? There's 3 of them.
6.
3 times 6. This tells me what?
It's an ion.
It's an ion, and
How many electrons there should be in the structure?
how many electrons there should be in the structure?
In the structure.
There's only supposed to be 1 electron in there? Or are you saying we're adding an additional one?
Oh, I thought you were talking about the 4. I thought you were talking about the 4 plus the 3 plus the, you know, thing.
Oh, I was talking about the minus that I circled.
Yeah, but that means that there should be 1 additional electron in the structure.
Oh, so we're adding an additional one. Okay. And hydrogen?
Is
6.
1.
Yeah, hydrogen is 1. Okay, so altogether, that's going to be a total of how many electrons?
24.
So we're going to have a total of 24 electrons. Okay, so we had 4 that are going to be around carbon. Better. You see my. Okay, we have 3 oxygens. We have a hydrogen. And we have an additional electron. Let's put that right here. Okay,
Okay.
so can we work this so that everybody has 8?
Yes.
Okay. When you guys do that, and then I want you to calculate the formal charge.
Okay.
Okay. Anybody want to give me their thoughts? Or take over my board? Nobody? Alan? Are you there?
Yeah.
Okay, what do you think, Alan? Sounds like you're doing the same thing that I'm doing.
I am. I'm on my lunch right now.
So obviously we have C in the middle. Can I have a bond here?
Yeah.
Okay. What about a bond here?
Double bond.
Double bond. Okay. So you mean I'm gonna drag this over here. So, but that, does that give me 8 around that oxygen?
Yeah.
It does, because I have 2 right here, and I have 4, 6. I don't think that's quite 8.
No.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24. So that one don't quite work out right over here. So, what about a triple bond? I can't do a triple bond, or can I?
No.
No. So this structure is not looking so hot, is it? So what about if we do something like this? And then we'll throw that extra one here. And then we have
Yes.
that one will work.
Yes.
Okay. Okay, so then we have O. Does that look good, Alan? Let's count our number of electrons. Altogether, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that matches up. What about 8 around all of our other elements except hydrogen? 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around this oxygen, and 2, 4, 6, 8 around the carbon, and we got 2 around the hydrogen. Does that work for you? And then we want to put it in brackets and put a negative charge on it and call it a day. Piece of cake? Yes, no, maybe?
Yes. But I'm guessing that since there's an extra electron, that shows up in the double bond that you made, because we can't just put a random electron somewhere, right?
Well, the thing is that this tells us that we have an electron there.
Yeah,
So the fact that electrons are moving, it can go anywhere. Right?
but
Because
what I'm asking is that like a bond is two electrons, but that's okay if there's like it's better to have one more than to have one less, I guess. If that makes any sense.
I'm not understanding.
Okay. So we made the double bond because there was an extra electron, right?
We made the double bond so that we can obey the octet rule and make sure that carbon had its octet full.
Okay, so where does the extra electron show up then in the structure?
So the extra electron showed up on this end with the, in this case, it would be with the carbon, because you had the two that were here that were given by the carbon. You have the other two that were given by the carbon, and then you have that additional one that's in that bond right there. Because if you look at this oxygen has 2, 4, 6, 8, I'm sorry. I mean 1, 2, 3, 4, 5, 6. It's sharing that one with the hydrogen that came from the hydrogen, and that extra electron that's represented by this one is being shared right here with that carbon.
But I guess I'm kind of just confused because wouldn't there be a bond anyways, even if there wasn't that minus sign?
No, because then you don't have enough electrons, and then somebody is going to end up short. You'd have 23, right?
Oh, okay. Okay. Yeah, I guess that makes sense because now there's an even number.
Mm-hmm.
Yeah, okay. Gotcha.
And remember, anytime you have an odd number, a total odd number of electrons, that means somebody's going to get shorted on an electron.
Oh, okay.
Okay, and it's always the guy who's the weakest with electronegativity.
Okay, gotcha.
Okay. 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 Okay, resonance structures. So in resonance structures, so let me tell you about isomers first, and then I'll tell you about resonance structures. So an isomer is a chemical that has the same chemical formula. So this is the stick structure for fructose, though I haven't finished drawing it. And each of the corners represent a carbon. So that's 1, 2, 3. Okay, so the chemical formula for fructose is C6H12O6. The chemical formula for glucose is C6 H12O6. Fructose is a 5-ring sugar. 1, 2, 3, 4, 5. Glucose is a 6-ring sugar. 1, 2, 3, 4, 5, 6. Okay? I call it a ring because it forms a circle. That's the ring part of it. Okay? So, do these guys look exactly the same?
Kinda. I can't really tell by your drawing.
Can't tell by my drawing. Look at this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.
No.
Okay, so they don't look anything alike, right? One's a 5-ring sugar and one is a 6-ring sugar. Okay, so, but they have the exact same chemical formula, right? So fructose is mostly found in fruit, right? And glucose, that's found in beets and stuff like that. Okay, so they also have different tastes. They have different properties. One reacts better, one is easier to break down than the other. Glucose is actually easier to break down than fructose is. Okay, so they have different physical and chemical properties. Okay, but they have exactly the same chemical formula. Okay, do you guys see that? Yeah, no, maybe.
Yes.
Yes.
Okay, so the definition of an isomer is two compounds that have the same chemical formula but different chemical structure. Okay,
Okay.
did you guys kind of get that? So that's an isomer. Now, a resonance structure is just the movement of electrons so that you have a different bond structure, right? So let me show you. So look at these three. Call that one A, B, and C. Okay, so we have 3 different structures here. Are they the same? And if
Yes.
they differ, they are the same? Are they the same chemical structure?
I want to say that they are, but I don't know.
So the chemical formula is exactly the same, right?
Yeah.
And structurally, these guys are kind of the same, right?
Mhm.
So this up here is called a resonance structure because it's the movement of electrons. Now you notice that's your 1 oxygen, that's your 2 oxygen, and that's your 3 oxygen. What is the difference between A, B, and C?
The oxygen.
What about it?
So one has 6, the other one has 4, the other one has 8.
So what do you mean by,
The electrons,
okay, so this one has how many around it?
6.
And this, how many bonds?
1.
And this guy, 3?
Wait, why 3?
Well, this is 3, right? I said this is my oxygen 3.
Oh, okay, yeah.
I'm just giving it a name,
Okay.
okay? So what about number 3, oxygen number 3? How does that differ from oxygen number 1? This is oxygen number 1.
The bond?
How many bonds? What is this called?
Two bonds?
It's called a double bond, right?
So,
A double bond, right? This is a single bond. This is a double bond. If there are 3 lines between it, it'd be a triple bond.
okay.
Okay. So you're right. Oxygen 1 has a single bond. Oxygen 2 has a double bond. Now the difference between these guys compared to say this structure B is where that that double bond is located. The double bond is located on oxygen 3. Where is it located on structure B?
Two.
On oxygen 2. Now, what this is showing you partially showing you that you could have 3 different structures where the electrons are moved in different places because the electrons are mobile. They're constantly being moved around. And so at any given point, you could have this structure existing, you could have this structure existing, or you could have this structure existing, right? And so that's basically what a resonance structure is. It's just that movement of that electron so that you're forming a double bond in a different position, okay? Where here it was on carbon 3, on hydrogen 3, on oxygen 3, here is on oxygen 2, and here would be on oxygen 1. So do you guys see how that differs from an isomer?
Mhm.
Okay. So let's say we have something like this.
Khalid, please leave her alone. Khalil, déjala, please.
Okay, so we have A, B, and C. So which ones are resonance structures of each other and which ones are isomers to each other?
I think it's the last one has a double bond between the 2 sulfur atoms. So does that mean that it's not a resonance structure?
That is correct. That means it's
Awesome.
not a resonant structure. So this guy would be an isomer to these 2 guys.
Okay.
These guys are resonance structures, A and B. So those are resonant structures. And then C and A and C and B are isomers. Piece of cake? Back there? Are you with me?
Yeah, I got you.
Okay, good. Okay, so electron pair geometry. This will be the last thing that we talk about. So with electron pair geometry, we're looking at, when we draw those structures, let's put up the last structure. We're going to be counting, yeah, let's do this. I'll draw a new structure. We're going to be looking at the center atom. So who's the center atom here?
The S.
Yes. And we're going to determine how many attachments it has, where electron pairs also count as an attachment. So this is kind of like having another attachment. So these dots represent like an attachment, okay? So how many attachments does the S have?
5.
So it would have 5 attachments, okay? What about this guy? What about that guy?
4.
Okay. Okay, so this guy has 4 attachments. So when it has 4 attachments, we would say the electron pair geometry would be tetrahedral. Tetra meaning 4, hedral meaning sides. So it acts as if it has 4 sides. That's with the electron pair geometry, okay? Now, the electron pair geometry helps us also understand the angle, because when you have 2 electron pairs too close together, they're going to be pushing each other apart because they want to get their distance. They want to make sure that they have enough distance between them. So those pairs are going to, you have 2 pairs to try to push each other as far away apart as possible. So in the case if you have 4 attachments, the furthest away, since it's a 3-dimensional structure, would be an angle of 109. And I'll show you that here in a second. 109.5 to be exact. So the angle between all of these, sorry, that thing up there and this guy, is about 109.5. Okay? So if I have 3 attachments, and remember, a circle is 360. So if I have 3 attachments, let's say, and when I talk about attachments, I mean things that are okay. So like in this case, that double bond doesn't count as 2 attachments, it only counts as 1, because there's only a single attachment between carbon and that atom there. So that one would have 3 attachments. So if it has 3 attachments, what do you think the angle is if the angle of a circle is 360? I'm sorry, yeah, 360. So if I have 3 attachments, 1, 2, 3. So what do you think each of these angles are going to be?
$120.
120. So if I only have 2 attachments, so we have something like, let's see, this guy. Okay, then what would be the, again, look at our circle, 2 attachments. What is the angle?
180.
Okay. So do you guys kind of get that?
Yes.
So let me show you a picture and then we'll stop for today. Okay, so that way you don't have to rely on my horrible drawing. So if it's tetrahedral, 4 attachments, 1, 2, 3, 4, then the angle is going to be 109.5. If it's, this guy is called trigonal planar, meaning it's all in the same plane. Tri meaning 3, gonal, trigon, so, and let me type that up. Then the angle is going to be 120. And then this guy is called linear. And the angle is 180. Piece of cake?
Right.
Or piece of pie?